Okay, so I'm doing homework 2 number 74. It starts just by saying a physics professor demonstrates the Doppler effect by tying a 600 hertz sound generator to a 1 meter long rope and whirling it around her head in a horizontal circle, kind of like a lasso, at 100 RPMs. What are the highest and lowest frequencies heard by a student in the classroom? So I started by drawing a basic diagram to show what's happening. So this is the classroom, the audience, and then this is the sound. So you have a couple of, first off, like things you know, your knowns. Let's get a different marker. So you have your first frequency, or I guess frequency initial, is 600 hertz. And then you're given here also the length of a string, so I'm assuming this is going to be useful at some point, so we'll just start by saying R of the circle is 1 meter. And then here it says the Doppler effect, so you know you're going to be finding F plus and F minus, or F approaching and F receding, so you have to find which one's F approaching and which one's F receding, if this were like one point in time and this were one point in time. So since this circle is moving this way, this is going to be F approaching the students, and this is going to be F receding the students. And then you're also given the rate at which the circle moves. So I'll just write that the circle is rotating at, I guess, at 100 RPMs. And R is revolutions per minute. So I'm going to make sure, so let's just underline that. And that's basically it for our knowns. So then we'll also start by writing out our fundamental equations that we know for the Doppler effect. So that is for F plus and F minus, and we know that F plus is going to be the higher frequency. It's going to be greater than 600, and this is going to be the lower frequency, so less than 600. And that means it's going to sound like, if it's less than 600, it's going to sound deeper bass, basically. And then we'll just write out our equations. So you have F naught is 1 minus for the approaching V of source over V. And then you have F naught is 1 plus V of source over V. This V is the sound or the speed of sound of air, in regular room temperature air, and since it doesn't specify what the temperature of air is, we're also just going to assume that V equals 343 meters per second, which is your regular velocity of sound in air. So if we had everything, we could basically just plug it into these equations and we'd find our lowest and our highest frequencies, and that'd be great. But it looks like we're missing one thing, and that is our V source. We don't know V source. So we have to start by finding the V of the source. Find V source. So we are given some key points here. We're given that it's rotating at 100 RPMs. And then we're also given that the R of the circle is 1 meter, or the radius of the circle is 1 meter. So let's look at my notes real quick. And we also know that V equals the distance over the time. D is the total distance the little ball travels in 1 revolution. And another way to describe this is basically the total distance is the circumference of the circle. So if you guys remember the circumference of the circle, where circle R, you're finding circumference, which is the entire distance over that one circle, is 2 pi r. This is 2 pi r. Let's just specify here that distance around a circle. So when we're writing out the final equation to find our V source, we're going to write out V equals, and we're going to start by doing 100 revs per minute, which is our given rate of how fast this thing is orbiting. And then you have to multiply it by the circumference over the revolution, because for one circumference, or is revolving, one revolution is one circumference, basically. So then you do the circumference, which is 2 pi r, over one revolution. And then we'll have minutes here, but since we want everything to be in meters per second, we're just going to convert from minutes to seconds. So you do 1 minute or 60 seconds. So once you solve all of that out, you get this number of 10.472 meters per second. I like to leave it in this many significant figures at first, and then once we're at the end of the problem, then we'll, simplify it down. But it's good just to reduce as much error as possible, so we're just going to do this part. I'm not going to box that because it's not our final answer, but v source is this. Okay, so we're back again. This time I just wrote out our v source up here, and I erased all the work, so I have enough room to do part 2. So now we're at part 2. We have everything we need basically to solve for the f approaching and the f receding. So let's just start by writing out our base equation, which is f approaching. We'll do that first. F naught 1 minus v source over v, and we know that v is 343, v source is 10.472, f naught is 600 hertz, and you just plug that in. And then you solve for f approaching. So 600 hertz over 1 minus 10.472 over 343 meters per second. And you get your f approaching equals 618.86 or 619 hertz. Is going to be our higher frequency. So we'll circle that. And then we'll move over here to do our f receding, which is just f naught over 1 plus v source over v. And then you plug it in again. 600 hertz over 1 plus 10.472 meters per second. Over 343, and then we have f receding equals about 582 hertz, which is the lowest. So that basically means when she's doing the lasso, when that little speaker is at the back of the room, furthest away from the students, they're going to be hearing the lowest frequency at 582 hertz, and when the speaker is the closest to them, they're going to be hearing the highest frequency at 619 hertz.